Today we'll discuss probably the simplest method of designing an FIR filter, and that is using the window method. So the method begins with an ideal filter. You would probably lay this out in the frequency domain. An example that we often use is an ideal low-pass filter. And then, using the inverse DTFT, you analytically determine what the ideal impulse response is going to be. So here we are with the ideal low-pass filter being a sinc function, which of course has infinite duration. And the next step is going to be to effectively truncate that to something that we can use. When we do the truncation, we have several options. One is just to say we're going to only take the first so many samples, or in the case of a symmetric filter like this, maybe we truncate and only keep the samples -20 for n equals -20 up through n equals 20, and that's what we do. It turns out, however, that this truncation approach isn't the best, that there are some smarter things that we can do. And step 2 generalizes truncation into something we call windowing. Okay, so windowing then looks like this. We would have h of n is equal to h ideal of n times w of n. And w of n will have some finite extent. So essentially we're multiplying most of h ideal by zeros, and the middle part we multiply by 1 for the truncation case, or something that works better is to multiply it by a tapered window. So tapered windows work best. The Hamming window, shown over on the right, is an example of a tapered window. Although not shown, it would be 0 outside this interval, and then 1, or not 1, but non-zero just only inside the interval. The Hamming window, named after Richard Hamming, gave an interesting talk about various things, how to succeed as a scientist, and as part of that talk he mentioned how to get things named after you. He has the Hamming window, the Hamming distance, and several other things named after him, and that's just for 0 less than or equal to n less than or equal to n minus 1. So I'll show you some common windows, and then we'll get an idea as to why this works the way it does and exactly what's going on. So here we have the Hamming window. It's a solid line. Another one called, it's often called the Hanning window, but it should be the Han window. And I can see here, even in this semi-official description, we have the Hanning. It's really the Han window, the Blackman window, the Bartlett window. They're all tapered windows, and the rectangular window is a little hard to see because it's just 1 over this interval and then 0 outside. So if you want to do straight truncation, you would just multiply the signal by your rectangular window. All the samples in here are retained, all the ones outside are eliminated. And the same thing happens, of course, with the other tapered windows, but the tapered windows modify the impulse response in the middle. One to note is this Bartlett window is also called the triangular window. So Bartlett triangular window. Most people don't know the phrase Bartlett, and this is often called the boxcar window. So now you know. There's a few. There are actually many different windows that you might choose. So what goes on when we multiply a signal like our ideal filter by a window function like this? Well, we would have that if we have h of n is equal to w of n times h ideal of n. When we take the Fourier transform, we have h of e to the j omega is equal to the convolution of, oops, that should be a w e to the j omega convolved with h ideal e to the j omega. Now this is a continuous convolution, so it's done with the integrals, and we can visualize what goes on in this manner. So here we have an ideal filter shown, and in such a manner. Of course, it's a DTFT, so it will be replicated in frequency. Let's just focus on the stuff here over on the left. So what's going on here is that we have the impulse, or rather the Fourier transform of our window function, highlighted here in green, and we have the Fourier transform of our ideal filter, shown here as an ideal, perhaps low-pass filter. When we convolve those two functions together, this window function effectively is going to blur the ideal filter. And what we end up getting is shown down below here. And you might notice that this little bit right here looks a lot like that right there. Okay, so there's a little bit difference going on because we have this convolution changing things a bit, but you get the idea that this little node here, each of these ripples is going to be controlled in width by that. In other words, the wider this peak, and we call this the main lobe, the wider the main lobe, the wider the ripples are going to be up above, and the more gradual the transition between the main lobe and the first zero crossing, the more gradual that transition is going to be down below. So how can we impact the shape of this to get perhaps a closer fit with our FIR filter? Well, one way we can do that is by our choice of window functions. So different window functions are going to have different characteristics. If we look at the things up here, it turns out that our rectangular window is going to have the fastest transition from up above to down below. Our transition region will be the steepest. Steepest maybe is a better word for it. Something else to note, though, is that we overshoot. We don't go down to zero, we go beyond it. Now when we're looking at the magnitude response, this is going to bounce up. And this is called a side lobe. So the rectangular window has the fastest transition region, but also the highest side lobes. So in its race to get down to 0, it overshoots. And as a result, we may have a really good transition between the pass band and the stop band, but the stop band is going to have a really high ripple. There's nothing you can do about that. You can make your rectangular window longer. It will still have a ripple just as high. The ripple will be more narrow, but it will be just as high. For a rectangular window, that's 13 dB down. On the other hand, if you go with something like the Hamming window, then you get a more gradual transition region, and in particular your main lobe is wider. But the side lobes are small. So that's just two windows. What about the triangular window? The triangular window is kind of in between the rectangular and the Hamming in terms of its response. So there's a variety of different windows that you can choose. Which one should you choose? If you just want something quick and dirty that will work, most people use the Hamming window. It's not ideal for all circumstances, but it's kind of just a good old standby. It has reasonable main lobe width, it has good side lobe attenuation, and it's simple to calculate and apply. So it's very commonly used. So here's some comparison of an actual design and how things work out. Looks like it's a cut and paste job gone slightly awry. Okay, here we go. So in this particular case, we have an ideal frequency response over on the right, and this is showing a normalized frequency response, and so this would be my guess is that they've normalized this so that this is pi and that's minus pi and that's 0. So we get an impulse response, an ideal impulse response shown on the left. And you notice that even by the time we're out at 200 samples, it still hasn't died away enough to disappear. So if we would like to create a more realizable version of this, assume then we can only have 41 samples, plus or minus 20, and we'll cut it off after that point. So if we use a rectangular window, we would essentially take that where most of the filter energy is, and we'd multiply the rest by 0, and then we could look at the frequency response of that particular system. And what we see is that we get this green curve over here on the right. Of particular note is that side lobe there, which is up there pretty high. Also note that this transition speed is fairly quick. If we multiply the whole thing by the Hamming window, we end up getting a slower transition to its lowest point. Instead of hitting the first 0 here, it hits the first 0 here. However, we are way down there. That got us much further than we did before. We'll actually run into Windows designs, or Windows again, when we do the DFT and some types of frequency analysis. But the long and the short of it is, if you have an ideal frequency response, find your ideal impulse response, multiply it by a window such as the Hamming window, and you'll have what you like. One other thing that needs to be brought out, though, is what does the effect of the window length have on it? Well, if we were to look at the frequency response of our windows, they get narrower and narrower as we have longer versions of the windows. So essentially, by going with a longer version of the window, we get a sharper transition region. On the other hand, the side lobes remain at the same height, but they move in closer. So longer windows don't change the shape of the, they don't change how much attenuation you get, but they do make everything sharper and closer to the ideal in that respect.